Okay, so the topic of today's lecture is efficiency of learning and entropy production. So we'll try to see how entropy of the trainable variables affects learning. So let's start with a hypothesis. Now, learning is more efficient when there are more available solutions for the trainable variables. And then it would be easier to find them. So it seems like a logical assumption. Now, in the language of thermodynamics, it means that there is more entropy in the trainable variables. So the more, the better. Now, this isn't going to be the whole of the story, and there'll be another part of it, because having too much entropy may not be good at some situations. But nevertheless, this is a good starting point. It's related to something that is known as Occam's razor, and that is something that we use when construct theories. Now, in the words of Isaac Newton, it says that we are to admit no more causes, and that would be trainable variables, of natural things than such as are both true and sufficient to explain their appearances. And the appearances are the non-trainable variables, something that the trainable variables are trying to explain or learn. So again, in the language of learning, it means that there should be either fewer variables or less entropy. And then if we have less entropy destroyed, then we have more variables available to find new solutions. And so you used up fewer variables to explain whatever you've been learning up to this point in your learning dynamics. And then therefore you have more entropy or more trainable variables to learn something new. New doesn't mean that it has to be a new data set. It can be finer details of the data set that you've already learned. And that brings us to the principle that we already discussed that principle when we derived how the learning system behaves near equilibrium. Now here we're going to be applying this further way of equilibrium, like in the very beginning when you just start learning. It seems that it's beneficial for the entropy production to be stationary. Now that includes both. That includes, first of all, the statement is that the path taken by an optimal learning system, in this case, optimum meaning having the best possible architecture, is the one for which entropy destruction is stationary. Now, if I would say that entropy production is stationary. Now, if I said that entropy production is minimal, the smallest, that would be equivalent to the Occam's razor and to the hypothesis that we have. Other way, if entropy production is maximal, so if we have more. Now we have to be careful because entropy can be either production negative or positive, and so there will be two limits that we'll discuss. Now, however, this principle is a bit stronger, and it kind of tells you that, well, in some situations, it may be the minimal entropy production, and some it may be the maximum entropy production. And we'll discuss those two limits, exactly when they realize and how they're related to the phenomena in learning that we know about, such as overfitting. So we'll try to relate overfitting to the situation where you have too much entropy in the system, and underfitting when you have too little entropy in the system. And then you're trying to see what is the best architecture for you to actually be like in the sweet spot, right in between the two limits. And what is the quantity that you can calculate? So you construct a neural network. You don't do any calculations. You calculate a certain quantity. You look at it and says, "Oh, that looks good. That has a right value. So there is a good chance that my neural network will perform well." And we'll see that the deep network are in that direction. So they are better performers. They are satisfy this stationary entropy production better as opposed to the shallow ones. So we'll demonstrate exactly why that happens. Now, the one step we're not going to take here that can be taken is to see, all right, but out of all neural architectures, which need not be deep or shallow, or maybe unconstrained, like we discussed before, what would be the best one? And that is the question that will depend very much on the boundary conditions, but however, nevertheless, there'll be some general statements you can make. Okay, so that's the setup of the problem. Now let's redo some of the calculations that we did, but we are going to do it in the limit where the drift is dominated over diffusion. So before we wrote down the Fokker-Planck equation and had two terms. It was very similar looking, but there were two terms, one that represents the drift due to learning, and then the other one that represented the diffusion due to the stochastic nature of algorithms. Here we neglect the diffusion, and we say, all right, let's just concentrate on learning first. Then you write down something that is known as a continuity equation. Basically, it tells you that the probability distribution over trainable variables, just like before, has to satisfy this continuity, meaning that probability shouldn't appear out of nothing and disappear into nowhere. So there has to be conservation of probability. So on the left-hand side, we have a partial derivative with respect to t. On the right-hand side, we have this partial derivative with respect to all of the trainable directions. That can be your weight matrices, biases, all collected together. And then you have this term where you have the velocity of the drift times probability. Now, the velocity of the drift, we assume that is in the direct, just like before, in the direction of the gradient of the free energy. Now, free energy of the non-trainable variables we've shown is equal to the df is equal to du TdS. So I'm just substituting here. And at the same time, and now in this one equation, you see two forces that act on the trainable variables. One is the learning force that just takes the system in the direction that would minimize loss function. And the other one is an entropic force. It would take the system in the direction where there are more states. Given these two forces, they may act in the same direction, they may act in the opposite directions. In the equilibrium, they would balance one another, and so df would be 0. But we are away from equilibrium, so we may think about both of them. Now, the one thing I'm going to make an assumption here that gamma is less than 0. That is, again, something that may change depending if, like, maybe there is a limit where this learning force is just negligible and everything is governed by the entropic force. And then the value of gamma in this effective description may be something else. But usually we do think about this as something which is less than 0, just because this first term is what you are ideally want, is what responsible for the minimization of the loss function. Okay, so gamma is less than 0. This is our equation. Let's now look at the main quantity, entropy production. Entropy production is given by this. So it's ddt of the entropy of the trainable variables, which is negative integral of p log p. And what I do here is take this ddt inside the integral, and then there are two terms to differentiate the p, and then the other one, the factor is log p, or to differentiate log p. And then if you differentiate log p, you get derivative of p divided by p, which is canceled with other p. And then you get this integral of dkq dp dt. So this term is 0, just because now I can pull out ddt from the outside to the outside of this integral, and what you will have inside is integral over the probability distribution over all trainable states, and so that's always 1, and derivative of 1 is 0. So that that goes out. So the only thing I have is this term where dp dt I've already calculated. It's given by the continuity equation. So all I do is now plug for dp dt this expression. And so this is what it is. There is a minus sign now, cancelled with this minus sign, you have a gamma. Okay, so what to do next is consider a situation where either your trainable variables are compactified, and then when you differentiate by parts, integrate by parts, there's no boundary term, or when the probability distribution goes to zero in infinity. And that's a good assumption if you think about Q's and B's as weights or biases. Basically, they always stay, within zero. They don't go to infinity. And so that assumption is good of vanishing probability distribution at the infinities. Okay, so now we do differentiation by integration by parts, meaning we take this derivative and switch it to the log p. When you differentiate with log p again, you have derivative of p divided by p, which is canceled with this p here. And so you end up with this term and a minus sign because of the integration by parts. So that's your final answer, but you can massage it a little bit more and take the derivative of with respect to p back to f, and so do the integration by parts once again, and then you get this expression. And that's an interesting expression, actually. That's the main result around which we're going to be discussing today, because what it says is, apart from this gamma factor, what you have here is a Laplacian of the free energy. So this is the sum of the second derivative of free energy, but now average over all states, all state weighted by the probability distribution. So you can think about this as an expected value of the Laplacian of the free energy. Now, remember, when we discuss the probability distribution of the trainable variables, what we really mean is that we imagine there is many computers, and you may start with all the same initial conditions, but then because of the stochastic gradient descent, because of the random number generator, they all go to different states. And so there'll be a distribution of the states of those computers or the states of the trainable variables. What it says here that the entropy production, growth in the entropy, will depend on what the Laplacian is of the free energy. And of course, one way to do it is to do many runs of this learning task, have many computers, or even if you just do one run, and then that one run you measure what the free energy Laplacian is, that will tell you what happens with entropy. Is it growing? Is it decaying? And that will tell you how the system is performing. And remember, in the previous slide, we argued that this ds dt has to be stationary. And so for it to be stationary, we need to understand what, and the entropy production very much depends on this term of Laplacian free energy. So do we want the entropy production to be maximized, or do we want it to be minimized? And so here there are two limits that I will quickly discuss, and then we'll dig into details about what things happen with the thermodynamics of the trainable variables. So let's take the first limit. Let's assume that you've done this runs, you calculated your free energy. It may be a difficult task, so maybe you've done it in the Gaussian limit. Then you took a Laplacian over the trainable variables, and you obtained the result that the delta F, the Laplacian of the free energy, is actually positive. Okay, so if that is positive, and given that gamma was negative, that means that the entropy is decaying. So it becomes smaller and smaller. You can imagine a space of trainable variables, and then it's kind of anti-diffusion is happening. So the trainable variables all get to like isolated locations, and there is isolated minima where they get stuck. Now that's pretty bad, because what it means that the system at some point will stop learning, right? It will just start clustering around some isolated places for the trainable variables. Entropy will continue decreasing until it goes to zero and the learning terminates. Now, we don't want that to happen. And for that not to happen, we want to have an architecture where this Laplacian is zero, or maybe as close to zero as we can. And if that is the case, then you really have lots of flat directions along which you can go, the trainable variables can go and explore whether there is a way for them to improve further the learning. Okay, so that's one limit. That's when this entropy production is actually negative, and when the system has a danger of being stuck in a local minima. Now let's consider the second case, which should not be overlooked. Now, what you have here is you have a greater than zero entropy production. So it seems like you're getting more and more solutions possible. So there is a lot more states in the queue, in a possible queue. But and then that means that you have lots of runaway solutions, and you may explore that phase space, and then you may be getting to solutions which have nothing to do with the actual data set, but only have to do with a particular subset of the training data set. And then you would see lots of overfitting, which we also discussed earlier, related to the fluctuations in the loss function. So loss function will be greatly fluctuating, is not doing very well. Okay, so yes, you do want a lot of entropy in the trainable variables, but not to the cost of having it too much, such that the actual solutions become diluted, and then you may never end up finding them. Okay, so before we move on, let me see if there are any questions that you'd like to ask, either about the hypothesis and the proposed principle of stationary entropy production, or about the calculations that we've done here, and how it is kind of important, because here we've related entropy production to something very concrete, the free energy of the trainable variables. So we can go ahead now and actually calculate. So let's see if there are any questions. Okay.
By trainable variables, are you including also like parameters on the optimizer?
Yeah, that's a good. Yeah,
because I feel like that would also impact the dynamics.
Yeah, it's a very good question. So there are hyperparameters that can be potentially included in all of these calculations. And if you do have them, then you want to treat them at the same level as trainable variables. Sure, you should include them. Now, it would be harder for you to do all the calculations maybe analytically, but you can still do it numerically, estimate what the free energies is, maybe do a few runs, and then understand in which direction you should be deforming the state of the system. However, here, my main assumption was, let's forget about hyperparameters. How to incorporate them within the architecture, it's a different question, so let's just put them aside. Let's fix them. And now let's say the loss function is fixed, the learning rate is fixed. And now still, what would be the more appropriate architecture, like shallow versus deep? When would you want to do one or the other, or maybe unconstrained? And so that now the question is more about, and then as we'll see, it's mostly related to the weight matrix that determines this free energy. And a little bit of the bias, because biases determine average value of the activation function, and I also contribute to the expression for the free energy, and therefore to the entropy production and to the learning efficiency. Other questions? Okay, so let's do this calculation. Not calculation, let's continue the analysis, right? So we know what the free energy is. We already...
excuse me.
Sure.
In the previous slide, where did the negative go? There was a negative gamma, and then it became positive.
So this negative gamma?
The last line, yes, right there.
From here to here, right?
Yeah.
That's by parts, right? So you move this derivative to the other.
Oh, okay.
Yeah, so there was a couple of times when I had to switch the sign. So every time you do by parts, you switch the sign and ignore the boundary conditions. This is valid when the probability distribution goes to 0 at boundaries.
Oh, okay.
Sure. Okay.
Got it. Thank you.
Sure. So let's see what we can tell more about this free energy. So free energy seems to have an important plays an important role in this consideration. So let's see what it is. So we know in the equilibrium, and we discuss it, that's what happens. dF is equal to du minus TdS equals to 0. And so once system gets to non-equilibrium, the dF stops changing, at least on average, and then this expression is correct. Now, however, this is not all the story, because if you remember, this equation came from the fact that we modeled U as a function of Sx, of just entropy of the non-trainable variables. Of course, you can also model U as a function of the trainable variables, and then take not just U with fixed trainable variables, but over ensemble of the trainable variables. And then basically, from the point of view of this equation, it means that you are not in equilibrium. There's still one more parameter that needs to be added in your thermodynamic description. And so let's here add one more parameter, just the entropy of the non-trainable variables. Okay, not their number. We could have put here the number of trainable variables. It's all okay from the point of view of thermodynamic description. But here, let's concentrate on the entropies. Now, their two are related. Usually, you have more trainable variables. They would have a totally larger entropy. But here, we are really interested in the entropy, so we keep this as a parameter. Then the averaged change in the free energy isn't 0, just as it would have been in equilibrium. And so it would be proportional equal to something like TQ TdS. And then there may be more terms here. So whatever you want to include, you want to include the number of layers, they can go here, whatever it is that, whatever the parameters. Remember, in thermodynamic description, it's relatively simple. You just choose whatever the macroscopic parameters you want to keep track of, and then you model your average loss as a function of those parameters, and then you can write down this expression. Okay, now so dF doesn't is no longer 0, but is given by this, and that is valid at early times. So at late times, things equilibrate, and the system will go to 0. And the dF will go to 0, but early times, this is an interesting limit that we can analyze. Now, if dF is equal to TQ dSQ, then ds dt, change with respect to time, if we assume that now this temperature of the trainable variables is fixed, would be given by this. That would be an expression. This would be equal to this, where this curly equal sign comes from the fact that we haven't written down all of the macroscopic parameters. There may be others. Okay, so that's one side of the story. And the other side of the story of the it has to do with the microscopic calculation that we've done on the previous slide. And so ds dq was shown to be equal to this. Now, why this is interesting, because that tells you that the change of the free energy with respect to time should also be related to the Laplacian of the free energy. And now in this, and by looking at this middle, the right equations, this right equality, we can try to guess what should be the right values of the TQ, such that the system does behave according to the stationary entropy production, and it goes to the state where Laplacian is closer to 0. Well, look, we know that gamma is negative. And we know that, and then we can combine these two terms in this one equation, and then move TQ to the other side. So if gamma is less than 0, now if we want this to be a diffusion-like equation for F, or heat equation, more appropriately to say, and we want in the longer limit, we want this Laplacian to go to 0. We know that this TQ has to be negative as well. Then negative TQ multiplied by gamma gives us a positive coefficient, and then solution of this equation of the first order in time, second order in space, the system would go to flat uniform distribution, not distribution, uniform state for F in the regime where TQ is negative. And in this case, in the long run, our Laplacian of the free energy will go to 0 or closer to 0, and the conditions for the stationary entropy production would be satisfied. So that would be an agreement with the principle that we imposed. Now, before we move on, now of course we don't know whether this is really happens. I must say, because you may come up with an architecture where this is really positive, okay, and if it is positive, then it's anti-diffusion, and then really this Laplacian grows. It's anti-like diffusion equation, and then Laplacian grows, and it's not close to zero, but becomes further and further away from zero. And according to our discussion, previous discussion, this is a bad regime. That's where overfitting or underfitting would take place, and people and the system would not perform as it should. And that's one result from this simple modeling. This is thermodynamic modeling of what the loss function is, or what the free energy is. Now, the other thing to note is when TQ is negative, which is dF ds, what it tells us is that the free energy decreases if we put more entropy in the trainable variables. And that makes sense. If you put more and more trainable variables, you would want, ideally, your system to perform better, loss function to decrease, or free energy to decrease. Now, if this doesn't happen, then let's say this would have been positive temperature. If it was a positive temperature for the trainable variables, then the opposite would happen. And then you would put more trainable variables, and the system would start performing worse and worse. What is it? That's overfitting, right? You put more trainable variables and doesn't behave as well. Now, how to resolve it? It has to do with, again, your free energy, with the structure of your neural architecture. You want to make sure that this T is negative, and then no overfitting takes place. Now, also, on this page, we discussed the thermodynamic perspective, and then it makes sense, right? So you have some non-trainable variables that are held at some positive temperature, and then you really want that temperature to decrease, and so you put it in the contact with the trainable variables, which are kept at low temperature, and they decrease the temperature of the trainable variables, and therefore reduce its loss function. Questions? Okay, so let's move on. We can come back to this. This is, again, just a phenomenological description of what might be happening, so that we have an idea of what kind of signs and dependencies we want. Now, remember, the free energy is still something you can calculate either analytically or numerically. And then SQ is something that you calculate analytically and numerically. And then you can run a test and say, oh, well, okay, here it is. I know what's the problem is. My temperature is positive for the trainable variable, so it doesn't do what it should do. Okay, so now let's do this calculation analytically, and then we'll discuss some of the numerical results. Analytically, we argued that the free energy in the Gaussian limit, and this is the only limit where we can really write down the integral of the partition function and calculate what it is, has those two terms. The second term is not very important, just constant for a fixed temperature of the non-trainable variables. And this left side, the first term, is most important. It contains the G matrix. And G matrix is where all of the architectural properties of your neural network are sitting, right? So this is where your weight matrix is sitting. And so once you know what the weight matrix is, once you calculated the average derivatives of the activation functions, you can plug it in here and find this matrix and take its trace. And then from its trace, you will know exactly what the free energy is. And not only free energy, you can calculate all other properties, such as the Laplacian of free energy. Now, however, we have to be careful here, and we're going to do one step that is a little bit, may sound a little bit strange, but this is just because we want to push analytics as far as we can, not because this is exactly how we would be training on it. So what's said here is that we should treat the all of the eigenvalues of this matrix G as trainable variables. So we want to think about them as trainable variables. This is not exactly correct, and the right thing to do is to actually think about weights and biases being trainable variables. But nevertheless, this is the assumption that we're going to make that will allow us to do the differentiation very quickly. So that think about this: you're not training for the weights and biases. You're training for the right eigenvalues. Now, again, not the completely correct assumption. That would mean that all of the weights and biases are somehow connected together through these trainable variables. And so maybe the right thing would be to write is this lambda is a function of q's, and q's is a function of w's and p's, which is the assumption we're going to make. All right, so if that's the case, then we can easily, if we just say, all right, let's assume that the eigenvalues are what we are training for, then we can easily find the Laplacian, because Laplacian of first of all, the trace is just the sum of the eigenvalues of this matrix. Now, eigenvalues of this matrix are just nothing but the eigenvalues of the sum of all all eigenvalues of expression log 1 minus beta lambda I, and then all you have to do is differentiate it twice. So after the first derivative, log will become as 1 over 1 plus beta lambda I. The beta will jump in front, will cancel with this beta, and so you'll get that expression, and then you differentiate it one more time, you get that expression. And so now, by doing this, we've achieved a result that actually this Laplacian, if we are treating eigenvalues as the dynamical trainable variables, is actually negative. Okay, so if it's negative, now we go to the limit and say, all right, there is a danger of overfitting. We don't want it to be too negative, and we want it to stay as close to 0 as possible. Again, this is a Gaussian limit with all those weird assumptions. So once we do calculation, we still have to go to numerics and see whether that makes sense. Okay, so good. So we want the entropy production to be minimal. We should choose architecture such that this Laplacian of free energy is as close as possible to 0. Now, we want to make sure that what it is in initial conditions, whatever we choose for the weight matrix, but most importantly, we want to make sure that's true during the learning dynamics. That's what's happening. Okay, good. So now, before I show you results, so this is not numerics, but just to understand, to get a feeling of what happens with this. How would we go about minimizing? How would we go about making this Laplacian of the free energy as close to 0 as possible? As I already said, this Laplacian is negative. So if we are to minimize something, we want to minimize a negative of that Laplacian. And this is the expression that governs it. But now I'm going to equate it to something else. And here how the logic goes. So consider a very, very large weight matrix. There's many eigenvalues, and we want to understand how they shift around and how they move, and how to make architecture such that they can move in the direction that they should. And so to analyze that, we say, all right, let's consider only a small subset, small fraction of eigenvalues, and the fraction is going to be gamma, which is smaller than 1. And let's see for this, and let's assume that this fraction of eigenvalues all have roughly the same eigenvalue, lambda. So if you have lots of eigenvalues, then there will be a lot of eigenvalues next to each of the whatever scale you choose it to be. In fact, maybe I'll show you how the spectrum of eigenvalues look like. So it looks like this. So if you choose any region, there'll be lots of eigenvalues that are within this neighborhood, within this region. Okay, so the fraction of eigenvalues that we consider is gamma. They all have roughly a lambda as eigenvalue. And then let's write down what the free energy is. And then we'll try to see negative of the Laplacian of the free energy. And then we'll try to see where eigenvalues would have to move so that to make it as small as possible. And by making it as small as possible, we would make the entropy production as close to zero as possible, and so there'll be no overfitting, and we'll be in this sweet spot. Okay, so if you do these calculations and you do it for the feed-forward network for which determinant of G is equal to 1, then you get this result. There's just some function which depends on lambda and gamma. Remember, gamma is the fraction of eigenvalues we can consider. Lambda is the value of the eigenvalues. And I just plot here for some examples. So n equals to 854 is a choice that was taken for this number came from the fact that the numerical simulation that I'm going to show you after that were run on the MNIST data set. Gamma 1/3 doesn't seem to be much smaller than 1, but it's again something that allows me to draw those plots and so to make the point so that they look like something that is represents the dynamics that we're interested in. And then I plotted for 4 different values of beta. Remember, beta is something that actually changes with time. Beta is the inverse of the temperature of the non-trainable variables. And so that as temperature decreases, beta gradually grows. Okay, so that's the setup. And now let's see how this function changes with time. So remember what the system wants to is to make sure that the eigenvalues change. Optimal architecture should be such that eigenvalues change to make this as small as possible, right? So make a gradient Laplacian of the free energy, negative Laplacian of the free energy, or Laplacian of the free energy to be as close to zero as possible. So this is the initial conditions. Think about this. So this is the state of the system in the very beginning. This graph as a function of eigenvalues is given by this. Okay, so if some eigenvalues start here and they do want to make the Laplacian to close to zero, then there should be a valley where they will roll, and so the eigenvalues will try to roll to the left and keep going to the left. And by doing this, the Laplacian of the free energy will be as close to zero as possible. Now, if this graph, let's say I've constructed this graph, if I had something like parabola, then what it means that the system would be stuck in some place where the Laplacian is relatively large and it cannot decrease further. Here it can, so it just has to roll to the left, and then it will go exactly to zero as it should, as it want to be. Now, however, with time, and so initially it can roll without problems. The eigenvalues can roll to the left without problems, but with time, this is how it changes. So the left side keeps raising, and so at the long run, there is no more runaway minima on the left, and the system becomes stuck in the minima. There is a point where inflection point happens, and so this time you're still okay to run to the left, but then there is a hill grows, and so it's like a barrier, and it doesn't allow you. If eigenvalue is stuck here, it will not be able to move to the left, and eventually it grows large enough, and so the whole dynamics terminates. And then you cannot make your dynamics better. You cannot make this Laplacian of free energy closer to zero. The learning terminates at this point effectively. Okay, so now let's observe all of this dynamics through the simulation. So remember, we've done this calculation showing what the Laplacian should be. Now we said, okay, well, how will the eigenvalues evolve if the network is good? If it allows it to have this linear, and the statement was, well, whatever your neural architecture should be, it should have this possibility to go to the left. If it has this possibility, then it will be an efficient learner. Now, if you have architecture that doesn't allow you to have this runaway solutions to the left, then it will be a poor learner, and basically you will get frozen at a given temperature, and dynamics will still happen. And now I'll show you the results of 2 simulations. One is I already showed you those graphs, but now it's in the context of the efficiency of learning. So one is for the shallow network, and the other one for the deep network. So in both cases, you will see that some of the eigenvalues will want to run away to the left. So here where they start, so it's basically from -2 to +2. This is a shallow network. We already discussed, and we'll talk about this more, it's completely symmetric. And so, yes, some of the eigenvalues try to move to the left, but they don't get far. And so basically, in the initial conditions, you have something like this. After training, you have this, peak emerging in the middle. But the system is completely symmetric, and so you do have runaway solutions on the left, but those runaway solutions don't go far to the left and get stuck there. Now, however, if we now take a look at the deep neural network, so you also have some kind of more or less symmetric solution in the beginning. Well, actually, symmetry is already broken even in the beginning. But what's more important, the symmetry of this log of the matrix G is even more pronounced at late time, more pronounced in the late times, and then eventually you'll see this gap formed of the eigenvalues that actually had time to run away to the left, and those that got stuck and cannot run further on the left. Remember, this is exactly what was our prediction, that first you will have this runaways, then there'll be some heel formed, and so if you didn't escape to the left, you'll forever stuck to the right. And at this point, there is no more advantage for the eigenvalues to slide to the left, and they get frozen. And that's what you see here. However, a huge difference between the shallow and the deep network is that in shallow, because of the asymmetry of this distribution, because of the skewness of the distribution, it was possible for those eigenvalues to run on the left. Or for the shallow, they also tried to do that, but because of the symmetry, every eigenvalue on the left was attached to every eigenvalue on the right. So we didn't model this attachment in the analytical analysis. We assume they're all independent and they're free to change as they want. And presumably what you would have in a completely unconstrained network, but this one is not unconstrained, it's very constrained to be shallow. Okay, so before I show the results that prove why the shallow network has this symmetric spectrum and therefore not efficient learners, and deep they do not have the symmetric spectrum and therefore are efficient learners, let's see if there are any questions.
Is there any threshold when a network becomes deep? Like how many layers?
Yeah, we'll talk about this. So basically, the calculation that I've done analytically, and I'll answer this question in a second. So basically, the point is the deeper it is, the more unconstrained it becomes. But eventually, of course, you're right, when it becomes too deep, then there are other constraints that come into the game. And so maybe you will allow to have the asymmetric spectrum, but there'll be other constraints that prevent this runaway of eigenvalues and therefore reducing the value of the loss function. So yeah, so there not a threshold. The calculations that were done are just for very shallow and the very deep, and then there was arguments saying why not completely shallow, but few layers is not as good as small layers. Yeah, I'll answer this question shortly. Other questions?
If you continue the training, will you see more gaps, or is it just one?
No, they're frozen. So this is the whole point, right? So this is red line. You just got to the point where there is no more advantage of, here it was advantage to rolling to the left. Here there is no advantage. Yeah.
Okay, got it.
Other questions?
Do you have intuition as to if this would change for attention-based layers?
Good. No, for now, no, but we need to discuss it. So that's a good question. I do have intuition about unconstrained. Basically, intuition is the following: like in unconstrained, all the eigenvalues are free to be whatever they want to be, right? So they're not attached to this. So imagine there's like strings between those eigenvalues that just hold them together, and then you are not free to roll where you want. So I think whatever other constraints you have in the system, they're always bad, unless those constraints kind of represent the intrinsic symmetry of the system. So, for example, convolutional layers, right? So they're good, not because there's still constraints, right? When you have convolutional neural network, but they're good constraints because they kind of tell you, well, don't learn in that direction because that breaks your underlying symmetry, something like that. So if something like this happens with attention layers, where there is something that comes from the training data that tells you, well, this is relevant, this is irrelevant, and so put constraint on the irrelevant information as much as you can, but do not put anything on the relevant information. Then we would know exactly what should be the architecture.
Okay, yeah, I see. Also I had a question on like a few slides back about the Gaussian limit. Yeah, here, like what exactly are you referring to in terms of like the Gaussian limit?
Okay. So
I think I missed something like
right.
very basic.
So this, yeah, that's basic. So basically, this calculation is only correct when you have non-trainable variables, states of neurons, which you can have large number of neurons, but they are modeled by a Gaussian distribution, which is completely wrong at late times. Late times, we know that each neuron like develops two peaks. They start classifying, so Gaussianity breaks down. But the limit of Gaussian is what allows us to make these calculations and write the answer. Now, what we would want to do, of course, even at late times, represent it not maybe one Gaussian, but many Gaussians, and then would still be able to do calculation. Now, the expression of the free energy will be more complex. Now, Laplacian would be more complex, but that would allow us to carry on analytical calculations and see what happens. Yeah.
Okay, so this kind of breaks down when you start training. So it's
Yeah.
basically like an initial.
It works well in the beginning, right? So you want to reduce
okay.
the loss function very well, right? So this, start learning efficiently, and then the other thing come into the game. So the symmetry breaking starts taking place. The Gaussianity starts breaking. But actually, next time we'll discuss exactly what happened at that point. So it's actually a good question because it connects this lecture to the next lecture. In this lecture, where early on we're trying to see, all right, you should not start with a bad architecture because you will never start learning well. But once you start learning that, and once all this phase transition takes place, this is a criticality regime. So this is when you do have lots of flat directions and you have criticality. Well, you want to continue learning anyway, and how to do that, and what kind of statistical description of the system at those late times as appropriate is something we'll discuss next time. Yeah, well, that's early on.
Okay. Yeah, thanks.
Yeah, this is early on. So basically, analytics early on. This is early on, but that's late. So that's already this is already a limit where I cannot do analytics or using the Gaussian limit. But I see that features that were present when the analytics was appropriate are still there. You still see the runaway to the left, and you still see those gaps. Okay, so good. So and that's actually a very standard strategy in physics and sciences, right? You do calculations for toy models, then you say, well, I mean, what if it works in the more complicated case? Let's test it. You might not be able to do it analytically, but you test it experimentally, and if it works, you're saying, okay, well, that explains it. So maybe that deviation from Gaussianity are not important for that particular calculations. Okay, good. All right, so yeah, so let's dive into a little bit more mathematics and try to understand what is it that's so different between the shallow and deep networks. Well, from numerics, from what we see is that the two important statistical parameters are the variance. We wanted to have large variance. We want the eigenvalues to spread out. But we also want to have a large skewness because we know that the important spreading out is for the eigenvalues to get to the left, for logarithm to get to the left, meaning that eigenvalues are going to get closer and closer to zero. That's what we want to be happening. And so another question is for the why is it that your shallow network and deep network both have large variance, but only the deep network that has a large skewness. Okay, well, so let's start from the not, and so this is called the second moment. You can talk third moment, first moment. Of course, moment only if you think about separate eigenvalues as random variables. I might refer it as moments, but of course, this is exactly what it means. Okay, so the first one is mu1 is just trace of the log of G. Well, that will be always 0 because trace of the log is log of the determinant. Now, determinant of the product of two matrices will be the product of determinant, and each one of them will just be equal to 1 because of the nilpotency of the weight matrix. Okay, so that's simple. So that doesn't really change regardless of whether you're dealing with deep or shallow. That's all the same. You just have this. Now, it will change once you have unconstrained, right? So for the unconstrained networks, the matrix is not nilpotent, and so you can have additional non-zero value here. All right, so now, but let's see what is so different about shallow networks. Very shallow. So I've taken the very shallow network such that it has only 2 layers. And so if I take, so input output, right? So not maybe the one that I was comparing numerically. Numerically, there was one layer in between input and output, but in general, you can have a very shallow when there is input and output and nothing else. Now, then the square of the weight matrix will be just B0. Whether you take the weight matrix multiplied by the diagonal matrix, that doesn't change this fact. And whether you take a transpose, it also doesn't change that fact. So the squares will be 0. Now, if that's so, then it means that thinking about this as one matrix and this as the other matrix, those matrices cannot appear one times the other without the other one in between. They have to be all mixed up. And so here is an example of what you can have. You can have starting with this F prime W matrix, then you're multiplying by a W transpose F prime matrix. And then this is a function. You can have terms of a number, arbitrary number of those products of those two matrices, but they have to be alternating one after another. And if you have that at the end, you must have this matrix, which is F prime W. Or basically what it says that all terms here are the ones that start with F prime W and end with F prime W. And all terms on these terms, they all start with the W transpose F prime and end with the W transpose F prime. Those are the two options, because this is the only matrices out of which the log G is constructed. What this F1 and F2 are is irrelevant. But what is important here, because of that, this first term would be traceless and the second term would also be traceless. Both of them will be traceless. And that kind of reconfirms the fact that mu1 has to be 0 in a weird way. Okay, fine. But that makes one more statement here. Now let's assume that we actually take this and multiply to an arbitrary odd power. Okay, so arbitrary odd power. Now, if we do that, then let's see how many. Now we have this product of two numbers. You can think this and that. When you raise it to the arbitrary odd power, each element will be a product of those two terms. But since the product is odd, there'll be unequal number of the terms of the first type and the first of the second type. And since there'll be unequal number of them, that will also be a traceless expression. Okay, so basically, you can also, in physicist context, you can think about this as a raising and a lowering operators. And basically, if you have an unequal number of raising and lowering operators, that will just be 0. And so that's what we reconfirm here. And that is exactly 0, not small, but exactly 0 for the shallow network that has only 2 layers. Now, but let's generalize it. Let's kind of not put it 2 layers, but let's allow some kind of layerness, but not too many layers, maybe 3 layers. Then what will happen here again, every terms where you have W, which takes you up, and think about W transpose, which takes you down. So every term that has lots of terms that take you up and in a row that will eventually reach the output layer, that will be set to 0. And so maybe here we'll not have a quadratic expression equals to 0. You have cube here equals to 0, but still this terms, the shallowness will eliminate a lot of terms and prohibit a lot of closed loop of the odd power. Not all of them, because there'll still be allowed closed loops of the odd power, but many of them will be suppressed. And so and basically you can convince yourself that even if you don't have this expression, the other terms would be suppressed. Here it is completely 0, but in the case of not so shallow, it will not be completely 0. And so you will have a little bit of skewness, but not large. Okay, questions? And the other thing I want to add here, you can just check it numerically, right? Create 2 neural networks with the few layers and many layers. The number of neurons can all be the same, and then check what this mu3 is. And when it's small, when it's large, and you'll see that the shallower it is, the smaller it is, and it's very, very small. And the larger it is, the larger it is. Again, there are other moments, there are other mu's that may be relevant, but at least this thing is very important if you want the runaway eigenvalues to move to the left, and therefore the Laplacian of the free energy to be remains closer to 0. Okay, so let's summarize. So that's what we know. We know for the shallow networks, mu3 is smaller compared to the mu3 for the deep. Now, Laplacian is further away from 0. This is in Gaussian limit, where it seems to be we are looking, making sure that this system doesn't overfeed. Now, the entropy production is less stationary, so it's further away from 0. Now, and then therefore learning is less efficient. So this is just the result of the considerations of the stationary entropy production principle. Now, for the deep networks, the opposite happens. The skewness will be larger. The Laplacian would be closer to 0. So lots of free flat directions where they can go explore and look for other solutions. Those flat directions are extremely important and will be the main topic of next lecture. And we'll show that those flex directions are responsible for criticality and scale invariance of the distributions, which are essential for learning. So this is, if you don't have that, your system isn't capable of learning.
Excuse me.
Yeah.
Since you care about flat directions and criticality, why did you not consider kurtosis, which is a fourth moment? It tells you about thickness and flatness of the distributions.
Oh, you mean consider higher moments, you mean, right?
Yes. Yeah.
Oh, yeah. Oh, absolutely. Yeah. All that is needed to be done. Here it's like the minimal analysis showing what is it that you need for deep, and that's what I'm kind of have here. What about unconstrained networks or networks with other constraints, right? Let's study what are the other spectral properties of the G matrix, which are later translated in the spectral properties in the free energy, right? So that it's connected, right? So you have weight matrix. From weight matrix, you calculate G matrix. From G matrix, you calculate the free energy. From free energy, you calculate its Laplacian. Okay, and so once you are done with all this, for whatever constraints you imposed in the beginning, you can see, all right, so now you're in business. Now we want to calculate all the statistical moments, mu1, mu2, mu3, mu4, and see what they are. Now, here it only was demonstrated that mu3 has to be large, okay? Well, it doesn't mean that mu5 shouldn't be large. Maybe to increase and make mu5 larger, maybe you should forget about deep networks and introduce recurrences and things that are present in unconstrained network. In fact, the one thing was important, these calculations, that you don't skip layers, right? So if you do start skipping layers, then even this analysis is not correct. So that's another thing important to lay, because you may have a feed-forward network, but it's not like from one layer it goes to another, from the other to another. Maybe you can have skipping layers, and that contributes to your. Remember, trace calculates kind of closed loops, and so to see all of the closed loops and to see whether it's possible to have odd closed loops, for that, you should consider other architecture, and they're all important. Yeah, absolutely. Okay, but at least for the shallow versus deep, mystery is clear here. Just one is a lot more constrained than the other. You can also think about this as an intuitive way, right? So imagine you had a large neural network, and it just without doing any calculations, by looking at the spectrum of the G matrix. You say, okay, this matrix is constrained, and this one is not constrained in a way that here you have eigenvalues that are attached. If it is, plus something, that has to be minus something, log of it, plus something, minus something. And the other one is unconstrained. It's clear that unconstrained, intuitively, it should be clear that unconstrained ones allows you to transform the matrix in a more way, and the space of the solution that it explores is larger. And so even by doing that, you could have convinced yourself purely numerically without doing any analytics that, look, I mean, this one has more freedom. But I agree that we have to look at the other moments to confirm that maybe there's something important hidden there as well. Other questions? Okay, so this is all I had for today. So let me just go over what we're going to study next. So the next is self-organized criticality and scale invariance. That is something now you don't see in the beginning. Actually, in the beginning, there is no such thing. And then this self-organized criticality and scale invariance is in the trainable variables. So you start training, your spectrum may be okay, maybe it's not symmetric, but there is no scale invariance. And so you will see that eventually it will develop for the good architectures. And then again, why is it important for learning the scale invariance? And then we'll discuss some arguments suggesting why it is essential. And remember, in physics, scale invariance is a very important concept, but it only happens when you really fine-tune your parameters, where the system is at the phase transition between different phases, gas, liquid, solid. Here, it seems that the system is always self-tuned to be in the phase transition, so it's always critical, and then it always changes the state from one to another. So those phase transitions happen all the time. Now, coming back to the distribution of the non-trainable variables, I said, like in the beginning, there will be one peak, and it will be very Gaussian. Then the peak will split in 2, and then in 4. All those are phase transitions, and there are many of them, and they're essential for learning, and they bring the whole system in this constant critical state. And so that would be the discussion. And then you can ask a question: well, how can I make my system get to the criticality faster, and how that can be used to enhance learning. And after that, we'll have more lectures on one more lecture on the emergent properties that has to do with autonomous particles, autonomous driving, and then something that has to do with the biological systems. And so if you can think about this as a lot more complex systems that are still happening, where happening in biology, we see that, and then we can ask the question, well, how can we do what we did before, like borrow some phenomena from biology and drag it into machine learning and make use of it, or other way around, take some no machine learning algorithms and see what they represent in terms of evolution of biological systems. There are no questions. I think this is it.